Welcome to the second part on the course on queuing theory. So we continue our exploration of everything you need to know about queuing theory. Last week, we saw a few operational laws, among which the very well-known law of Little's law. Today, we will start by studying the classical results for single queues. Single queue is a system where jobs come in and are queued until the policy decides that they are going to be served. So it can be a single server or multiple server queue. Here, let's start with the single server queue. A single server queue means that at any point in time, only one job is being served. So jobs arrive, they have a certain amount of work to be done. And under very general conditions, we have a theorem called Loin's theorem that appears to be trivial, but is a very useful theorem that essentially gives when such a queuing system has a stable regime, when it has a stationary regime. And not surprisingly, it is when the utilization factor, rho, is less than 1. Recall that rho is the arrival rate times the average service time. So here I should say a few things. The average rate is defined by considering the process of arrivals. So there are points in time when customers arrive. And the average rate is the long-term average, which, as we have seen last week, in a simulation can be estimated by counting how many customers arrive over an interval of duration t divided by the duration of the interval. Loin's result applies to theoretical processes. For a theoretical process, we assume that lambda is the expectation, which is the theoretical average, if you want, the expectation of the number of customers that arrive. Lambda multiplied by t is the expectation of the number of customers that can arrive in any interval of duration t. So the way I formulate it makes lambda very general. It's not necessarily a Poisson process, although many systems have a closed form when we assume they're a Poisson process. I'll talk about that in a few more minutes. Times the average service time. Average service time is the same thing. The average service time is the average that we measure in a simulation by observing how much time every customer spent in service divided by the number average taken over all customers here. So the simple result says that if rho is less than 1, there is a stationary regime. If rho is larger than 1, there is not. If rho is larger than 1, we know by Little's law that there cannot be a stationary regime, because if there is a stationary regime, Little's law tells us that rho will be equal to the probability that the server is occupied. Since there is one server, it must be less than 1. So that is easy. The natural result is that if rho is less than 1, the system has a stationary regime. It looks very natural, but surprisingly, if we take an arbitrary network of queue, not one queue, but a network of queue, it is not necessarily true that a network of queue is stable when the arrival rate multiplied by the average service time is less than 1 in every queue. There might be more complicated feedback-ish systems that make that more difficult. So in general, we cannot be as optimistic, but if a queue can be studied in isolation, this is certainly true. So that is the first reassuring result, which is very important because it gives us really a mental model, but is very, very often the case when we analyze a computer system. There are queuing points everywhere, and queues can be analyzed through the lens of Loin's results. Now, if we want to go beyond, we want, for example, to be able to analytically give the distribution of things we're interested in observing. What are the things we want to observe in a queue? Well, for example, the distribution of the number of customers, or the distribution of the waiting time, or the distribution of the response time. Waiting is the major thing that is unknown in a queue. When we have a queuing system, what we want to control, when we want to analyze, is what is the penalty of this queuing system, which is the waiting. For a special case of interest. Everything is known, at least in, perhaps not in closed form, but in theory. It is for the so-called MGI1Q. So this is a notation that you will see very often if you analyze literature on queuing systems. Such a notation has three compartments. The first one is a description of the arrival process, the second one of the service process, and the third one says more about the service system itself. So a number here means the number of servers. M stands for Poisson, probably because of Markov. So M here means a Poisson arrival process. So what is a Poisson arrival process? Well, there are different ways to define it. Probably many of you have heard about it in other lectures. The Poisson process can be seen in different ways. One way to say it is that this is a process where if I count the time between successive arrivals, then they are independent and are distributed according to an exponential random variable. So two things, they are independent and exponentially distributed. Independence means that if you had to wait 3 seconds between the first job and the second job, that gives you no information about what will happen for the following job. So that excludes, for example, batches of arrivals, periods of time where all of a sudden packets arrive or jobs arrive more closely together. This is not made possible with this model. We'll talk about how to model such batch arrivals a bit later in the course when we talk about modulated models. So here it is not possible. So that's the independence. And more than independence, the exponential distribution also means something else. It means memoryless. Another way to define the Poisson arrival process, which is more the physics way, consists in saying, I look at an interval of duration at the interval t plus dt. So an interval of time where dt is very small. And I observe what happens in this interval. So think of dt as being nanosecond or sub-nanosecond. Right? And I ask the question, how many arrivals will come in this interval? Since my dt is minuscule, there will be 0 or 1 arrival. Most of the time there will be 0. That's the most likely thing, because even if the arrival rate is very large, because my dt is minuscule, most of the time there is nothing. So there will be 0, perhaps 1, perhaps 2, it's not impossible, but the probability that there are multiple arrivals, as it can be seen with a bit more of work, is an O of dt square. In other words, it's order of the length of the interval to the square. So at first order, if I do a first order analysis, the probability that there is 1 arrival, the number of arrival in this interval is 0 or 1, and the probability that it is 1 is lambda dt. The probability that is 0 is 1 minus lambda dt, which is at first order 1. Right? But if we go to, at order 0 is 1, and at first order, we have this term lambda dt. Why do I do all this thing? Well, that's another way to think about it is to replace exponential distribution by Bernoulli distribution, or geometric distribution. Remember that geometric distribution is quasi the same as an exponential distribution, but where the values are quantized. The values can be a multiple integer of some quantum. For example, take the quantum being 1 nanosecond. If you count in integer number of nanoseconds, you will never have an exponential distribution because you will have something that takes discrete values. Although in practice, discrete number of nanoseconds is for us continuous at that time scale, but here, from a modeling viewpoint, it is discrete. So if we think of this as a geometric distribution, we can interpret the geometric distribution as follows. At every time slot, at every nanosecond, we flip a coin, and with probability that is approximately lambda dt, we decide that there is an arrival, and otherwise there is no arrival. And at the next nanosecond, we do the same thing again. We flip a coin again. That is exactly the discrete part of the Poisson arrival process, which is called the Bernoulli arrival process. The Poisson arrival process is the limit of that when the nanosecond goes to 0. So when you have truly continuous time. So an easy way to think about it is to reason in discrete time. So this is, then if we think about it in this way, the probability that there is an arrival now is lambda dt. And given that there is an arrival now, what happens in the next nanoseconds ignores completely, forgets completely the fact that there was an arrival now. So that means two things. Of course, the time between successive arrivals are independent of each other because we have forgotten everything about the path. But more than that, the fact that I have not seen an arrival yet, so I've been waiting for 2 seconds, I have not seen an arrival in this queue, that gives me no information about when the arrival will, the next customer will arrive. So having waited a long time does not give you better chance of seeing something happen. That is the memoryless property. Of course, in real life, we would not like things to have memoryless property. If I've been waiting for something long, I would hope that I need to wait less now. But this process, this memoryless process, has this property. This is used to model things that are homogeneous in time. For example, if you model the busy period at a server over the macroscopic scale, which is 1 hour busy period, for example. But if you model the packet arrivals in a system where packets arrive at lengths of gigabits per second, then that might be a good model where we can assume that at the microscopic level, the packet arrivals follow this Poisson process here. Of course, over time, the intensity will vary. So if we are at the busy period, the lambda is larger. If we are not at the busy period, it will be different. But typically, we concentrate on one stationary model for the arrival process. Then the GI for the service, so that we've talked about the arrival process. The GI stands for general independent. So general means it can have any distribution. It's not exactly any distribution. We require that the service times and the variance are finite. We will see a bit later in the course when we talk about fitting some models with infinite variance. That can happen in some cases of interest, and that would not fit in this case here. In fact, if the service time has infinite variance, there might not be a stationary regime for this thing. So G stands for general, and I stands for independent. Independent means that the service time of a job, a request, is independent of the service time of the previous request and of the next request. So one way to think about it, if you do a simulation, is that when a job is chosen to come into service, then only at this time you draw from a random number generator its service time. So that's one way to think about this process here. And one means there is one server, as we discussed before. So for this queuing system, there is an analysis that is well known, that is in the lecture notes. We will not do it. It's well known, but it's not so short, called the Polacek-Khinchin analysis that leads to those formulas, at least for averages. We can do more. We can do, at least in implicit form, we can find the distributions, but I'll just give the easy formulas. The first formula is N bar. N is number of customers. So the average number of customers in the queue, which is a time average. If I sample the queue at different points in time and I do in a simulation the average, or if I integrate, like we saw last week, the queue size measured in number of jobs over time divided by the total duration of my simulation, I would have an estimated of this, which is the the theoretical average, which is given by this formula. This formula says that the average number of customers in the queue is rho square. Rho is the utilization factor that we've seen in the previous slide, which must be less than 1 for this system to have a stationary regime, multiplied by kappa, where kappa is this magic number, is 1/2 of 1, and this ratio of the variance of the service time to the mean service time. So this is S bar square, this is sigma square sub S, so which means the variance divided by the service time square. So that is also sometimes called the square of the coefficient of variation, because that's the scale-free quantity, which is the variance divided by the mean square. So that tells us how much variability there is in the distribution. If the distribution is close to constant, if all customers have the same service time or quasi the same, then sigma square, the variance, will be very small. So this number will be negligible. So this is the term kappa divided by y minus rho plus rho here. This is the celebrated Polacek-Kinchin formula. We also have the average number of customers that are in the waiting room. So the ones that including the server is given by the same term, the same figure here without the rho term. R bar is the response time, the average response time. So the response time is the waiting time plus the service time. The waiting time is given next, so the response time is given here. You see a formula that involves the mean service time, the utilization factor rho, and this same number kappa here. Of course, we see that it increases with kappa. There's minus rho minus kappa. If kappa is larger, the response time is going to be larger, presumably. And the waiting time is given also rho over 1 minus rho S bar times kappa. So those formulas, or take-home message, well, they are closed-form formulas. So if you have a system that can be modeled, roughly speaking, with independent arrivals, and you don't know much about the service time, but you're able to estimate at least the mean and the variance of the service time, then this is how you could obtain at least a theoretical number for the average numbers and average times. In the previous formula, we saw that there is an equality between n bar and n war w, right? There's only a rho term added to the second one here. Do you think that this is specific to the MGI1Q, or is it more general, or is it specific of Poisson arrivals? Time for a little quiz. I close the poll in 5 seconds. Closing now. And the majority says the C, third answer, which is correct. This is again Little's law. The number of customers in the system is the number in the waiting room plus the number in service. So this is true at every point in time. So it's true for averages, of course. So n bar is n bar w plus the average number in service. And we saw from application of Little's law, which is called the utilization law, that the average number of customers in service is rho. So this is not a surprising formula. Congratulations to the majority. Let me come back to the MGI1 formula. If you look at all those formulas, there is something remarkable. They have on the denominator 1 minus rho, which is exactly a symptom of stability for rho less than 1. So here it's saying if rho is less than 1, it is stable. But we see also that when rho gets close to 1, then all those formulas will go to infinity, which is exactly describing the instability. When rho gets larger, closer to 1, then the average number gets very large. So that is one of the symptoms that we will need to remember about queuing systems. Here's a small catalog of other queues. You have in the lecture note a number of results, and you can find them also on Wikipedia for a number of queues. But essentially, we will see in this lecture the results that are fairly simple and that are, let's say, the first set of basic results that can be very useful. Perhaps the most used queue, because it's the simplest to study, is the MM1 queue. The MM1 queue is a special case of the one we just saw, when the service time itself is exponential. So it's general independent, plus specifically we add the assumption that it's exponential. So exponential service time, remember the exponential distribution has the memoryless property. So it means the service time is also memoryless. So if a job has been in service for 3 seconds, that doesn't mean that it's more likely to finish in the next second than if it had been in service for 20 seconds. So that's the exponential property of the service time, which is or is not true, depending. Many systems don't have this property, but some systems do. And so those of you who perhaps saw such results on maximum entropy in an information theory course, if we know nothing about a distribution other than its mean, then the information theoretic distribution, the distribution that we should pick, the one that maximizes entropy given the information that we have, is the exponential distribution. So if we know nothing about the distribution, this is the model we use. Now this model is can be studied exactly. That's an important model that is studied, for example, on a course on Markov processes. And we can compute everything, not just the averages in closed form, but also, for example, the probability that the number of customers in the queue in the stationary regime is equal to k is given by this simple formula. So we see that it is a geometric random variable. The average number of customers in the queue and in the waiting room are given by this, which is of course exactly the formula that we had before, with the value of kappa equal to 1, because the coefficient of variation of an exponential distribution is exactly 1. So that gives those simple formulas that are not new. They are just the ones we had from the previous case. What is new is the distribution here of the number of customers that has an exponential random variables, and also the probability that the response time, so the distribution of the response time, the CDF, is given by this, where you will recognize also an exponential random variable. So everything is known in closed form, from where you can get also easily, for example, the variance of the number of customers and the response time. So that's a system for which everything is known in closed form in the stationary regime, but there are also formulas for the transient regime. If we start an MM1 queue from a non-typical case, for example, as you do in a simulation, for example, from an empty queue, we can even know what is the probability that the number of customers is k at time t, given that at time 0, it was given from some distribution. But that's another story. The formulas are more complicated, but the take-home message is the MM1Q, we can do everything about it. That's why it's very often used. The MD1Q, D stands for constant, so that models another extreme. The MM1Q models what we do when we don't know much about the service distribution other than the average service distribution. The MD1Q is another extreme where we think that the service times are constant. They're all the same for all jobs, which are two ways of modeling when we don't know much. But it's important to realize the difference. If we know nothing about the service time, then of course the coefficient of variation of the service time is much less if it is a constant here, because the variance is 0. So we will have values that are less than for the MM1Q. Those 4 values here are known with exact values. We can know also things like the variance, or the standard deviation here, of the number of customers and of the response time. They have interesting closed forms as well. So those were single server queues, MG1Q, where we specify the service distribution. Here's another variant. This is a variant of the MM1Q where we add a 4th compartment with the number K. Capital K means the total capacity is capital K. So there are not more than K customers possible. Now, what happens when the queue is full? In this system, we simply assume that the arrivals are ignored. So if a job arrives when the queue is full, then it is simply ignored. Since there is memoryless property for the arrival process that will not impact the future arrivals. So this is a system with loss. When customers arrive, they might be lost. Here, we can analyze them with the same methodology as here. It's in fact simpler because it's a Markov chain with a finite state space, and we find the same formula for the number of customers. The only thing that changes the normalizing constant. Of course, the number of customers is between 0 and capital K, so the normalizing constant is different than here. So interesting is that the distribution of the number of customers of this is the same as the distribution of the number of customers of that, conditional to the numbers being less than capital K, which in general is not the case, but for this specific model is the same here. The normalizing constant eta can be computed by power series calculation here. And the probability, another interesting property is that this is a system with loss. So we might be interested in the proportion of jobs that are discarded because they found a busy system. All servers are, all the K, sorry, not all servers, the K slots in the buffer are occupied. So the probability that an arriving customer sees a full queue is also exactly equal to the probability that the queue is full. Well, you might say, well, this is obvious. Why is this a formula? Well, it may be obvious, but if it's obvious, it's because we confuse two things. Those two probabilities are different. In fact, if you look carefully, there is a little zero here. The zero is because this is not the same kind of probability as this one. This is an Palm probability. We'll talk about that in the last module of the course when we'll talk about Palm calculus. This is a probability that is measured, if we think of it in terms of metric. It's a metric that is not sampled at all in the same way as the other one. This zero here means this is a metric that has to do with measuring things whenever there is an arrival here. So if I do a simulation, I will have points in time when there is an arrival, and then I can specify, I can observe specifically things at instance of arrival. And then I can ask the question, if I look at all the arrival events, some of them led to a discard, some of them not. And then I can ask the question, what is the probability that an arriving event was a discard? What is the probability that an arriving customer is discarded? When I do this, it's a probability where I look at all the events. It's an event-based viewpoint. It's another way to formulate it. We take the event-based viewpoint and we describe metrics or probability from this viewpoint. The other probability here is a time-based viewpoint. Here we look at, in average, over time, what is the number of customers in the queue. So in order to estimate this, we would either integrate the number of customers in the queue, like we saw last week in a simulation, or another way to do it is to send a random inspector that would arrive, for example, every microsecond into the system. We'll ask the system, how many customers are there in the queue? We'll record this number, and we'll do the average of all the answers divided by the number of questions that has been asked. But here we ask at an arbitrary point in time. This is a probability at an arbitrary arrival. This is a probability at an arbitrary point in time. In general, they differ. But as we will see when we talk about Palm calculus, for Poisson arrival processes, they don't. Poisson arrival process and this type of queuing system, they give the same, which is very specific to the Poisson and the memoryless property. We'll talk more about that a bit later. But you could easily imagine systems where this is not true. For example, if the decision that somebody arrives is dependent on the size of the queue. If you imagine a queue where the more customers there is in the queue, the more customers are likely to arrive. So there is an attraction. Maybe in some mobility models of the road systems, you have models of this kind. If there are lots of cars in a given area, it is because there is something overwhelming that brings everything there. So it's more probable than others will come. So the intensity of arrivals increases when the system is more busy. Of course, for a queuing system, this is bad. If that happens, of course, we might not have exactly, this is not a Poisson process. So when a customer arrives, then it is more likely to find a busy system because most arrivals occur exactly when the system is full than in average over time. Voilà, those are three other typical single server queues. There are also simple formulas for some classes of multiple server queues. So MMS here means the same as MM1 before, Poisson arrival, exponential service time. And now I'm assuming there is more than one servers. For example, this is a very typical model for multi-core systems. Here, the utilization factor has a different definition. The utilization factor is the average number of customers in service. Since there are S servers, we rescale by S. So it is lambda S bar divided by S. So the average number of customers in service can be up to S. And this, of course, should be less than 1. So we find a similar result. And then you have other formulas because it's an exponential and Markov and the Poisson arrival. We can analyze that with simple Markov chain, which we can solve in closed form by using the theory that allows us to compute stationary probabilities for Markov chains here. And we find those formulas. And this, in particular, this formula here, which is the probability that all servers are busy, which is a probability that the number of customers in the queue is larger than the number of servers. This is a very well-known formula. It's called the L&C formula. That's, for example, the formula that was used in old days telephone systems, that is used, for example, in call centers as the probability that somebody is queuing. Presumably, in such a system, you have a number of servers because you don't want customers to wait, but you cannot guarantee that they will never wait. So here, the probability that you have to queue is given by this formula here, which is this number. So if you can live with the Poisson arrival and exponential service time for a system of S servers, the probability that an arriving request has to queue is given by this simple formula, which is known as Erlang-C formula. Voilà, that's all we'll see in terms of a closed form. We haven't really analyzed them. The fun part is really to demonstrate, to write the mathematics to demonstrate it, but that's not the focus of this course. Instead, in this course, we try to see what is useful in the theories done either in statistics or in probability for performance evaluation. So here is one of the very useful results that this tells us. It tells us about how our systems behave. If I can model my system by one of those, which means the arrival process is essentially independent of what happens in the queue, and then systems are being served. Then we see, for example, here I'm modeling a database as an MGI1 queue, and I'm plotting the mean response time versus the number of requests per second. Then we see in the formula that there is a 1 minus rho over the denominator, and that shows up exactly here. We see that as we approach rho equal 1, which is what corresponds to this value of the x-axis, the value explodes and goes to infinity. So this explosion, which is also what we call bottleneck analysis, right? If we are below the bottleneck capacity, things will be fine. Above it, there will be a problem. But it tells us also something. It says that the response time is non-linear. It's linear in the part where the server is very little, occupation is very small. So if I look at this fraction of the x-axis, then I could well model the average response time by a straight line. Right? It's very linear until at some point it becomes very non-linear. So for example, if the traffic volume increases by 10%, depending on where this increase of 10% is, the increase in average response time will be very small and proportional to the increase in this whole region, or very large in this thing here and increasing in a convex way very, very fast here. So that's the first take-home message. Queuing systems are essentially non-linear. They have this behavior. That's the really first snapshot to remember about queuing systems, they behave like this, which is very bad. This is the root cause of all the problems we have in computer systems, right? We would like to operate in the region where everything is linear and happening in a very smooth way. But if we don't control the load, if we go into this region, bad things will happen. Voila, little quiz. Here I have plotted analytically the mean response time for some system as a function of the utilization. And I've had three systems that differ only in the distribution of the time. So the GI allows any distribution. Here I have three distribution, one which is a constant service time, one which is an exponential service time, and another one that has larger coefficient of variation 2, which is, for example, a hyper-exponential distribution, or a Gaussian distribution with a standard deviation, which is 2 times equal to the mean here. Can you infer which curve can be attributed to which model? I close the poll in 5 seconds. 5 seconds to go. Gone. Unanimity on the last case, which is exactly the correct answer, because we know from the Polacek-Kinchin formula that the mean number of customers increases with the coefficient of variation. Well, in fact, this is our second take-home message, which is very general for everything in real life, but here is very easy to capture in queuing system. Variability has a cost. Randomness has a cost. So ignoring the randomness when we do some dimensioning or we take some decisions is completely wrong. This is a common mistake that is done by people who say, well, we have taken this decision, but now that we see what has really happened, if we had taken another decision, then things would have been much better. But this is, by doing that, this is ignoring that there was uncertainty and randomness. Here, this is exactly what happens. If you have a queuing system, then it's better if you find a way to make sure that the service time of all requests are exactly the same. If the average service time is the same, but the variability is larger, the average queuing time will be larger. Right? So in average, the server does exactly the same job, but the simple fact that the distribution of service time is taking very different values across customers will have a negative impact on the waiting time of every customer. So most variable service times increase waiting time. So this is known also in road systems, for example. If on a road system, the driving style has a huge variability, then that will increase, that will make the probability of traffic jams larger. This happens while at the same time, another thing happens that may appear contradictory, which is that the stability region is not dependent on the variability. The stability region, the region where the queuing system remains finite, is given only by the average service time. So that is a bit paradoxical, but the two are true together, which one way of thinking about it is if we care only about the catastrophical cases, then it's the utilization that matters, right? If you care about whether my system will explode or not explode, it's only the average time per customer that matters. If you care about more detailed metric about the queuing time, if you care about giving good quality of service to all customers, then the second order parameter, which is the variability of service time, starts to matter as well. Well, let's see another take-home message that we can see, which is called optimal sharing. With what we have seen, we can simply analyze two systems. So here I have a first system where I have two servers and an arrival rate of 2 lambda. I took 2 lambda to make things simple. And I take the same system, but I segregate them, right? So this is the queuing system of McDonald's or the post office. This is the queuing system of the supermarkets, right? You have at every queue, at every cash counter, you have a separate queue. So can we compare the two systems? So if we have a global queue or segregated queues, can we compare them in terms of response time and capacity? Well, I did it here. I showed on the x-axis the utilization factor, and I computed the mean response time for those two systems. How did I compute it? Well, we have seen the formula. This is an MM2 queue. So there is a closed form formula. And this is simply 2 MM1 queues. So there is also a closed form formula. So I simply apply the very basic formulas. I obtain this. Which one do you think is for system 1? I close the poll in 5 seconds. And the majority says the top curve, so system 1 is less good, which is not true. If it would be true, then McDonald's and the post office would not do it, hopefully, because at least post office, I'm not sure, but McDonald's, they care about customers. System 1 has a better response time, so it's the other way around, because the two servers are always available. In contrast with system 2, it may be that one server is idle when the other waiting room is not empty, right? So there is some inefficiency in this here. Of course, in reality, if you're at the supermarket, if the queue is empty, you will jump to something here. But if you don't jump from an empty queue to another, if you stay in the queue where you are, this is less efficient than that, because here you pool the resources, so you don't have servers that are idle when others are being served. So this is able to do less work than that here. Therefore, in average, the response time will be a bit better for this one than this one. So this system in general is more efficient. Of course, what happens is that if you look at the queue size here, you will see a queue that is probably at first order close to the sum of the two queues here. So you will have the impression that the queue is larger, but having a large queue doesn't mean that the waiting time will be larger. You also have to count the number of servers. It's better to have a large queue and 2 servers than 2 smaller queues and separate servers. In terms of capacity, which of the two systems has the larger capacity? So the capacity is the max lambda for which the system is stable, which in practice will mean the max lambda for which the queuing does not become catastrophically large. I close the poll in a few seconds. Closing now. And the majority says both have the same, which is exactly true. So again, this is an example where the capacity is not a first order quantity. If we apply the formulas we've seen before, an MM2Q is stable when the utilization less than 1, and MM1 is the same, and the utilization corresponds to 2 lambda over 2 S bar, and here over lambda over S bar. So both have the same stability condition. Voilà, those are a few take-home messages that are important about the qualitative behavior of queuing systems. So we have seen some of the formulas for some single server queues, which give average response time. Now, assume you model a system with an MM1 queue. That means you think that the distribution of the service times that you have measured is, roughly speaking, close to an exponential distribution. But still, assume there are some jobs for which you know more. There are jobs that will take a long time to be served and others that will take a much shorter time. In average, the mix of the job is such that it gives an exponential distribution. But still, we could ask the question, what happens to the large jobs, for example? What is their response time? So this leads to the question of what is the expected response time for a job or a customer when you know that its service time is X? Of course, in reality, you will know the service time after, but as I said, there might be cases where you can infer that for this kind of job, it's going to require a lot of computing cycles. So for example, its service time is going to be large. In a simulation, that would mean if we quantize X, for example, let's say for all the jobs that have a service time between 5 milliseconds and 6 milliseconds, I look at only those jobs, I measure the response time. In average, what do I find? I close the poll in a few seconds. Closing now. That was a more difficult question, admittedly. But the answer is fairly simple if we think that the response time is equal to the service time plus the waiting time. And if we make the observation that the waiting time is independent of the service time. One way to think about it is that one way I can simulate my model is by drawing the service time only when the customer is chosen into service. So if I write a simulator that has this form, then it becomes clear that how much time the customer will wait does not depend on the specific value of the service time, because the service time can be drawn only after the experience of waiting time has been done. So given that the waiting time is X, given that the service time is X, the waiting time is not affected, so its conditional expectation is equal to expectation, which is W bar, which is the average waiting time for all customers, which gives the second formula. Why do we talk about this? Well, because this is a system where the response time depends on the service time only through this sum of the service time itself plus something that is independent of the service time. So in other words, if you are a job that comes with a huge request onto the server, that does not impact your waiting time. Not all systems have this feature. There are systems where the queuing time or the response time will depend very much on the service time. And those are systems where the queuing is of a different nature, which are called the processor sharing queues. All the queues we have seen so far have what is called a queuing discipline, which is FIFO. So by default, when we don't write the queuing discipline, it means FIFO. We serve when the server becomes idle, we pick the next customer in the queue. The processor sharing queue is a different one, where there still is a single server, but all customers share the server equally. So if there are two servers in the queue, they get only 50% of the server speed, which means the service time, if the service time is 10 milliseconds and there are two jobs, then each of them will spend 20 milliseconds in service. So the time of service is given at a rate 1 divided by the number of customers in the queue. This is called the processor sharing queue. So this models at a very macroscopic level network links, for example. If the jobs that you're interested in are not microscopic job like a request, but an entire transaction, for example, a complete file transfer that will take perhaps several minutes, then if you're using TCP and you're sharing a communication link, by the fairness of TCP, at least if the round trip times are the same, the capacity of the link is shared equally between all the TCP connections. So this is a good model for, this is a good example where the processor sharing queue is exactly modeling this here. This is also used for multi-core systems when you have multiple processors by the same, and if the number of cores is very large, or if we have a time-sharing system in which the different processes are handled in parallel by all the by sharing the compute capacity. So this is another example of the MGI1 queue, but with a non-standard queuing discipline. Lorentz theorem applies to whatever of the discipline, so the stability is when rho is less than 1. But this system has completely different formulas that are very simple. The number, in stationary regime, the number of customers in the queue has this probability distribution, which is the same as for the MM1 queue. And the magic property is that you see here that it does not depend on anything else than rho, which depends only on the average service time. So this is an example of insensitivity. This is a queuing discipline where the distribution of the numbers of the queue, so the distribution of the queue size, is independent of the peculiar service distribution. In particular, contrary to what we saw before. Before we saw that for a single server queue, if there is truly queuing with FIFO queuing, any variability in the service time has a negative impact on the queuing time and number of customers in the queue. Here, it's not true. It's only the average that matters here. There are other queues that have this property. They are given in the lecture notes, but this is perhaps the most important one to which that happens. That's the first important result. Second important result, if we redo this conditional distribution exercise that we did a minute ago, if we ask, what is your expected response time given that your service time requirement is X, then the answer is it's exactly X divided by 1 minus rho. So if I plot, for example, the result we had for the previous queue, the FIFO queue, which is in blue, I plot the response time as a function of rho on the x-axis for 3 different values of the service demand, service time. I have a job that has a small service demand or a job that has a large service demand, then the total response time given this information will be larger in both cases. But we see that for FIFO, it's translated simply by an offset. We have the waiting time plus the response time, plus the service time. If the service time is minuscule, we see only the waiting time. If the service time is very large, we see like 10 here, we see 10 plus the waiting time. In contrast, for the processor sharing queue, this is not at all the same. The response time is proportional to the service time here. Here it's 10 times larger than here, for example. Which makes sense. If you have a processor sharing queue, that means that you have to share the processor between all customers that are present. So if you have a huge job, let's say a job that will last for 1 hour, during this hour, then it will have to compete with all the other jobs. So it's not like in a FIFO queue where even if the job requirement is 1 hour, then when it gets the server, it gets the server for this job alone. So this is a qualitatively very different property. And this is an interesting queue to model, for example, as we said, communication links or multi-processor systems, at least in simple cases. Voilà. This is all we will see for the theory of the queues. We have not seen much theory. I have given to you perhaps the most, the easiest queues for which we have closed form, so we can already say a lot. And then if you want a simple model of your system, you can use one of these queues. Now, what we will do is we will put all of this together to analyze a case study. And we will see how it is possible to do at least a quick and interesting analysis that will help us decide whether we want to do more. The question I'm asking here is, what is the impact of a capacity increase on a system? And what is the optimal capacity, in a sense that if we want to balance the cost versus benefit, what is the region where we have the most gain without a cost that is too large? This is a question that is constantly being asked for all systems you have to dimension. If you're dimensioning a data center or a service of any kind like Joe's shop, you will have this question. And in particular, if you think that in the next year or in the next month, your capacity will double, what should you do here? To make the thing more fun and in line with the season, it just snows on the mountain yesterday. So let's imagine this is for a skiing system. So in fact, this was motivated by some advertisement that we saw in the Lausanne area a few years ago. A few years ago, you had for Verbier, which is a popular Lausanne ski resort, you had this announcement that says 2 fois plus vite sur les pistes, 2 times faster on the slopes. Because, and if you look at the little characters, we said we doubled the capacity, débit doublé, throughput doubled. So we doubled the capacity, for example, by making a second parallel telecabin, or the speed of the telecabin is twice as much. So they doubled the capacity of the ski lift system, and they claimed that we would go twice as fast on the slopes. So the question that we ask here is, so here's my model. I want to evaluate the impact of doubling the capacity of a ski lift on the performance. So what are my factors? Well, the capacity of the ski lift, and in this simple model, I use a single number, which is how many people per second can the ski lift carry. And the metric, well, I think as a skier that what I don't like is the waiting time on the lift. I mean, the time spent going up is, of course, also important, but it's not perceived, at least by most people, if we believe economical studies, as the major annoying thing. The major annoying thing is the waiting time. So my metric I take as the waiting time. That's the thing I hate. So I want this to be reduced by increasing C. And the question more specifically, is it true that if I double C, I divide the waiting time by 2? As we have seen in the methodology part of this course, we need to have a well-defined goal, factors, metric, and a load here. The load for a ski resort is not an easy thing, right? And that you will find that very often in the mini projects when you will have to do an exercise on your topic of interest. Perhaps the load will be one of the things that will cost you a lot of reflections. Here, let me take 2 loads that may correspond to 2 very different things. Model 1, arrival in burst. So I go skiing on a Sunday morning. I wake up early for a Sunday morning and I arrive at 10 o'clock on the slopes. But there are thousands of people who had the same idea as me, and they were in the same train as me. So this is a burst arrival here. The other model is I'm a medical doctor and I go skiing on a Thursday, and on Thursday I go whenever I can, and I arrive in the middle of the day whenever I have free time. I use my car and I arrive at, let's say, 11 o'clock, and this is not the peak hour. So I will model that as the stationary regime. So we have seen different models. We have seen deterministic queuing. We have seen the MG1Q, etc. So this is giving us ideas for 2 different models. So let's start with the burst arrival. We've seen that the burst arrival can be modeled with a deterministic analysis. So I model my system as follows. There is the waiting room, which is where skiers are waiting. There's the gate, where this is when you go through the gate, you go up into the telecabin or on the ski lift, and then you go to the lift and you're happy because the fun starts. Now, we have seen how we can model this. Here, the key thing is to have arrival curve and service curve, or arrival cumulative arrival function and service arrival function. Here, the arrival curve, I assume, is a big burst. So in this extremely simplified, I have capital B people arriving at exactly the same time. Probably not exactly the same time, but well, they're leaving the same train, they arrive at the same time. So this, in this very simplified model, my arrival is a burst here, followed by no arrival at all, negligible arrival. Now, what is the service process? How many people go out? Well, as a fluid approximation of this, if the number is very large, of course, in reality, we have discrete steps. Somebody comes in, then the next waits, etc. But if things are fairly fast and the numbers are large, then we can simplify this by this linear model and say the number of people who go through the gate here is equal to CT, as long as there are people who can to be served that are in the queue here. So we will see this slope here. So this is my waiting, this is my service departure curve here. Now, what is the waiting time? Well, if I take the worst case waiting time, that is the waiting time for the last person in the queue. That's me usually. When I'm in the queue, my wife complains that I'm always the last for some reason. So that's a good metric for me. What is the waiting time? Well, we have seen when we talked about the playback buffer dimensioning exercise that the weighting with this method of analysis, the response time delay, is given by the horizontal deviation here. So this value here from this point to that point, that gives me exactly my waiting time here. Now, what happens if I double the capacity? If I double the capacity, C is replaced by 2C, so the slope is multiplied by 2, and everything is linear. We see that the waiting time is indeed divided by 2. So in this model, it is true that doubling the capacity will lead to a delay being divided by 2. Now, if instead of this worst case, the poor guy was at the end of the queue, we take an average case where you're one of the guys here, so in average you're at the middle, you draw a line at the middle, so the middle time will be the same. It will be less than this one, half of the value, in fact, but it will be also divided by 2. So in some sense, Televerbier was right. When they doubled the capacity, they divided this metric of the waiting time by 2. Now we can look at the other case, which is the person who arrives during the week on a not so busy day. And we could model this as an MG1 queue. Right? We see that we can think that the service time, if there's a single server here, we could imagine there are multiple servers that will not be very different. MGI-S queue, for example. But the property of that is that, as we have seen, the response time is very non-linear, which means that depending on where on the utilization we were, if we were there, for example, we come on a very idle day, not many people, doubling the capacity will probably, because we're in the linear regime, but we'll probably, and the waiting time is 0 when we're at 0 here. This is the response time, not the waiting time. I need to divide to reset it to 0 for truly the waiting time. Then doubling the capacity is probably linear when we're in this very low part of the curve. But on the other hand, we're in this part, the waiting time is negligible. So yes, it divides the waiting time by 2, but the waiting time was not perceived as a problem. So it's true, but not interesting. In contrast, if I arrive at a period here where we're close to the busy period, well, when I'm here, if I double the capacity, that means instead of being, for example, at a utilization of 90%, I will be at a utilization of 45%. So I will move from here, where the value may be very large, to here, where the value will be very small. So doubling the capacity for such a case, for a case where I was before the doubling coming into a congested system, will have an improvement way larger than 2. This is convex, so the reduction will be larger than 2. So this is what we could say with this model. But this model is probably too simple because in reality there is feedback in the system. If there is a large queue, then the skiers are spending most of their time, or a large fraction of their time, queuing. So they're not on the slope, which means also they don't come so often to go up. Therefore, the lambda, the arrival rate, is also less large. Right? So there's like a stabilizing system. A better model would be what we have seen, the interactive user model. We can close the loop by saying what happens. Another model of this system consists in saying, I have customers that come in, they wait at the gate, they go up in the lift, then they ski with some probability that's over for them, they go home, or they come back. And probably, except if the slope is extremely long, you probably come back and do it a number of times. So that might be a different model that is perhaps more realistic here. Again, the factors are the capacity C, and then we need to analyze this system. If we want a more refined model, we could say that how do we get the capacity C? Well, by saying if the gate has K slots, the time taken by a customer to traverse the gate is G bar, then we can see the capacity as K over G bar. So we can have more than one customer system, but still that corresponds to the same capacity field. And now the question is, if I have this closed system, what is W? How does W depend on C and on lambda? We have done such an exercise already using bottleneck analysis. So we can apply all the tricks that we have seen last week. I use Little's formula. The unknown lambda here, lambda is unknown because lambda depends on the fresh arrivals plus the recirculating users. And if the system is very fast, if there is 0 waiting time and the gate is very fast, the lambda will be larger and vice versa. So lambda is one of the variables to determine. We will have that this first formula, the average number of customers in the system, is the lambda times the sum of the waiting time, that's the quantity we're interested in, the service time here, and the think time. The think time is the time spent on the slope. So S and Z are given by, we assume, constant in this model. And the utilization, so that gives us this first formula, that W bar, our unknown waiting time, is equal to this formula, n bar divided by lambda. And in this first model, I could assume that n bar is fixed. So the number of people that are circulating during a given afternoon, for example, is fixed. Now we can apply the utilization rules, the two rules of bottleneck analysis. The first one, which says that the waiting time is 0 or more, and this will be accurate, will be close to equality when the system is lightly loaded, which means, for example, the gate is very, very fast. And the second thing, which is that the arrival rate should be less than the capacity, which is C, which is another way to say the utilization should be less than 1, which will be essentially close to equality when the system is completely saturated. If it's completely saturated, that means it's the gate here that dictates how fast you can do it. It's dictated by the capacity of the gate. So that gives us two, first inequality, W bar larger than 0, and W bar, which is equal to that, and the lambda being less than C gives me a lower inequality for W bar. We obtain those two inequalities for the waiting time here. That I can plot here. Now the trick is to plot it as a function of 1 over C, so the 1 over the capacity. That will give me this simple here. This is a straight line, this line, and the other one is W larger than 0. So this is my bottleneck analysis. I know that my waiting time will be lower bounded by this red curve. And I know that when the capacity is huge, that means when I am here, when W is small, this is accurate. And when the system is saturated, when C is small, so when I'm far on the x-axis, I will be close here. So I know that at the two ends of the red line, I'm probably exact. In between, I don't know. So if I don't know, I could do a detailed queuing analysis, which is what I did. This model that I gave can be analyzed exactly using what is called the theory of queuing networks, product form queuing networks. So we can have an exact solution. We will not see that in this course, but you have some more details in the lecture notes. So the key thing is that this class of networks has a closed form, a bit difficult to analyze in detail because it's a closed form with many summations to do. So there are algorithms to do the summations. So if I do a simulation, an analytical solution of the system, I find this, the red dots here. Sorry, I found the blue curve here, and the red dots are the bottleneck analysis that I gave here. So we see that, at least for this example, the bottleneck analysis is surprisingly accurate, which is a good case. There's no congestion collapse. Now, given this, back to my question, is Televerbier cheating on us? What is the impact of doubling the capacity on the average waiting time, if we take the blue curve as the curve of interest? What is your guess? I close the poll in a few seconds. Closing. Here we are. There's a tie. And the exact answer is there will be a reduction by more than 2 because this curve is convex. Oops. So if I take 1 point here, this is my capacity. If I improve things, I double the capacity. That means that the y over c, this is 1 over c, will be half of that, 1 over 2c. I am in the middle. Since the waiting time is 0 at 0, the curve is convex. That means that the chord is above the curve. So that means that the waiting time is below the chord. The chord gives the proportionality. So the waiting time is reduced by a factor more than 2 here. Okay, this was anecdotal evidence of using the different models that we've seen. But of course, it's more interesting than that. The main interest of such an analysis is that we're able to find first order statement about the critical capacity. We see here that the behavior of the waiting time is dictated by the bottleneck analysis, even though it's not absolutely exact, but qualitatively it's a very good first approximation. First, it doesn't increase very much, then all of a sudden there is a critical value at which it starts increasing. And this critical value can be computed exactly by the intersection of the red lines here, and it gives all, it's not very accurate, there's a whole region here, but it's close to this number, which is n over s bar plus z bar. So what is it? Well, it is essentially saying that you should match the natural rate at which this system would rotate, which is the number of people that are in the system, divided by the time they spend in one cycle. So this is how fast the skiers would cycle if there would be no gate. Now, if you match the speed of the gate to at least this value, then your customers will be happy. If you're below this value, then you start impeding on your customers. You start being a bottleneck to your system. And being a bottleneck means there will be unpleasant queuing. Voila. So that's what bottleneck analysis can give you, and this is how you can perform it easily for such a case. Of course, if you want more details, you would need to, if you want to simulate the queue size, the queue occupancy, you may need more sophisticated simulations, but that will guide your simulations in knowing that the critical capacity is here. So if you're already operating at this capacity, there's no point increasing, and that also tells you what you should measure to know where to increase or match your capacity. Voila, we're a bit early today, but this is how things are. So we have seen queuing theory. Again, queuing theory is a fascinating topic on which you could do an entire PhD, but I've delivered to you essentials in queuing theory, which are the laws, the operational laws, Little's formula, the utilization law, and the other laws that are extremely useful and very easy to understand. If you want to be a bit more sophisticated, you can use queuing models like we've seen MM1, MGI1, etc., all the variants of those. But you can also use bottleneck analysis and worst case analysis to give you good insights on where your system is going. Well, that's all for today for the lecture part. Next step for you is to test your understanding by doing the quiz on queuing. And in the following lab, you will be able to exercise in more details what happened in a simulation. Thank you very much. We stay online and see you soon.